Hello everyone, I'm Audit. Today I discuss some number theory questions in mathematics competition with my student.
Yeah, this is probably a counter example. It's probably not right. But,
Yeah, I said it's not, but you said it's true, right? Okay, what's your proof? What's your proof? Can you say again? I can write down your proof. Let's see. Yeah.
There's a common multiple between n and ab.
Okay, common multiple. Yeah, common multiple.
And the common multiple of n and ab can be split into prime numbers.
Common, not listed, right? It's just common multiple. Okay, common multiple.
Common multiple of n and ab.
Oh, N, A, B, three of them, right?
Two. AB is 1.
A and B are 1, right?
Yeah.
A and B are 1. Oh, that's just say a special case, right?
Oh no. What does it? I mean that A and B is one thing. So it'll be like a little
Yeah. Okay, can I write down something yet so I can see clearly? Wow, good thinking, huh? You said yes. Yeah, I just your proof.
It's one thing.
Yeah. So you said common multiple is
such a number can be split into prime numbers.
Can be prime number. Why? What's prime number?
So if we have any number, we can put it into a prime number. So like 2 to the power 3 times 3 or times 5 or something like that.
Okay. 2 times 3 or something.
So like it's just like an example. So we can probably get like well, what's the thing that can resemble a prime number? Is it like k times 1?
K times prime number. Prime number just except itself. The K is prime number. That means K don't have any factor greater than 1.
Yeah. Okay. So we can turn that into a prime number for an example.
Yeah.
It could be 2 to the power 3 times 5 times 7 to the power 2, right?
Yeah.
But then it could also be like a different number times a different number squared times a different number squared, or like a number to like the power of something times another prime number to the power of something times another prime number to something else, right? You can do prime factorization.
Yeah, you're right. Any number can do the factorization is the prime number times together. Yeah, you're right. That's a good rule.
So and because we know that, we can. So let's say that the common multiple is 2 to the power 3 times 7 to the power 2, right? Like what you've written here. If we say that A could have 2 to the power of 2 and B could have 2 to the power of 1 and 7 to the power of 2.
Okay. Yeah.
So A could have 2 to the power of 2 and B could have 2 times 7 to the power of 2. It could contain that. It's probably not that answer. It can contain that. It can like times another number, but it will contain these numbers.
Yeah. Okay, that's great. Okay. Now
and because it contains these numbers, will not be co-prime and will be divisible, I think.
Yeah, that's good. Okay. Now I'll give you a.
That was just making not co-prime.
Yeah, can you explain the concrete example? See, like for example, A equals N equals 3, A equals 9, and B equals 5. So in this example, so N is 3, right? 3 is divisible to A and B, 9 times 5. Yeah, so this is for this condition, right? So for this one. For this one. N is okay, now the last. Okay, yeah, for this one, done. But we need to check. N is divisible to A. So N is 3. 3 is divisible to 9. That's good, correct. So this one is 6. Or N is divisible B. Oh, yes. This is all. This is all.
Mhm.
Not and. If and it doesn't work here. So you're right.
Yeah. Okay.
It's divisible to 5. Yes.
Yeah.
This is yes.
Doesn't work.
Yeah, this is I saw this one is and. Okay, if it's and, it's not. Okay, so that means the factors of n must included in A and B together. Yes. So n must divisible to A or one of that. Yes, you're right. If I split that one, here, let me check. N, say n is 3 times 2. Okay, 3 times 2. Because A must include this one.
I think I know what I made a mistake in.
Yeah. Yes.
I think I might have proved that if we know that n is not co-prime to AB, then we can imply that n is not co-prime to A or and not co-prime to B. I think that's what I did instead.
Okay, yeah, that's another case, right? Yeah, okay, so n, see, because n can divisible to AB, so we can find another integer, say m. N times m equals AB. Yes, n times m equals AB. So n is divisible to A. Maybe between. Say n divisible by 9. 2 times 3. Yeah, you're right. Your math is good. Yeah. So this is 5. This is 7. Ah, I found the case. Let's count the case. Okay. So the example is the problem is 1n. Okay, you're not. Yeah, you're right. Okay, but one thing you missed. So 1n equals 6. A equals 10. And B equals 21. This case, it doesn't work. This is special case. Can you check this one? N equals 6. A equals 10. And this one equals 21. So n can divide, n is divisible to 10 times 21. But
yeah, it is.
n cannot, 6 cannot divided into 10 and also 21. This or that doesn't work. Did you see that?
Yeah.
Okay. But this one works. So even the or cannot work out. This is a counter example, right? Counter example. I think it must be not. So can you check your proof? So did you find this case? This is special case. So this one is 210, right? 210 can divide by 6. 3, 6. So this is 30. So this is 5. Yeah, 35. This is special case. It's counter example. Yeah, I found this one. It's very special. Okay?
Yeah.
In this case, this statement, yeah, this statement is enforced. Okay? Yeah. Did you think of this example?
No, I didn't really think of any examples. I just started off with a model and started doing it. But then I think what I did was that I found that they were co-prime. They were not co-prime, not that they were divisible.
Yeah.
I think that's the thing I made. That's the thing I stuffed.
Yeah, this is the case. This one doesn't work. This one
it can only be divisible if the number only contains those prime numbers and no other number.
Yeah. Okay. So in this case, none of that's correct. None of that's correct. Right? 10, 21, and this one works. Because how do I make this one? So 6, I made by 2 times 3, right? There are 2 factors of 6. But I give one factor to A, another factor to B. In this way, using this way, I can make this counter example. Yeah, that's it comes from. Got it? So for this one, it's not. Yeah, it's not. Yeah, this is counter example. If you can find the counter example, say this one must be not. Yeah, this one is didn't prove. You only proved it. I know that here. you prove that the factors of n, right, must included in the factors of A or B. But if it's just one factor from A, another factor from B, that's a special case for this one. Yeah, you have to think of this case. Yeah, you can write
So for this question, should I just write that it's not possible with the and then state it? What does it mean by salvage the statement?
I don't know. Salvage just means save something or something, right? I don't know this one. Save some statement, or maybe correct or something, right? So if I rewrite the statement, I should say.
Oh, I think what it means is that
Yeah,
it's. I think it's saying.
Yeah, or maybe the. Okay, if I say rewrite the statement, it should go other way. If n is divisible to A and n is divisible to B, then n divisible to AB. Go backwards.
Oh,
If we go backwards, the statement is true, right?
Oh, yeah. So it's something that. Oh, it's an irreversible thing.
Yes, reversible. Yes. So if we reverse, it's true. Yeah.
Oh.
Yeah, because this is the wrong way. Okay, wrong direction. Yes. Go reverse.
You can do that. Yeah.
That's it. Okay. Okay. Can I clear?
So,
okay.
Yeah. So for this question, I just state that statement and then I say why.
Yeah, that's it. Okay. That's the one question. Yeah. Okay. It's not.
And I'm still not too sure why.
Yeah. Go backwards. Yeah. Okay. This way. Yeah. Okay. Good. Yeah. Okay.
Yeah. I'm still not sure why the example 6, 10, and 21 wouldn't work.
6, 21,
6, 10, and 21. I don't know why it wouldn't work.
I don't know why.
I don't know why. Like, I mean, like, I know what I mean, like a proof of why the statement is wrong.
Okay, because you miss one case. This case you didn't mention in your proof. That's not in your proof. Yeah, you proved say all other cases, right?
Yeah, but what?
Say for
example, case standards?
N, yeah. So N is say N has all the factor, A has all the factor N has, right? So N divided by A divided by A. Or N has all the factors from B, so N can divisible to B. Yeah, that's two cases you proved. I know that. Yeah, I heard that you said, right? So if all the factors from N we can find from A, then N divisible to A. Or another way, N has all the factors from B. But for my case, part of the factor from A, part of the factor from B. This case you didn't prove. That's the problem. You have to say prove all the 3 different cases. You say N.
I stated that that B can take some and A can also take some.
Yes. Yes. So your case is
but
N.
I didn't consider
For example,
that.
E equals P times Q, right? So if A equals P times Q, then times the M, then N divisible to A. Or N, A is not this one, right? B is P times Q, that's case 2, times S. So N divisible to B. So that's you just choose one of that, or, right? So one of them must be correct. That's your proof. But you miss one of them is A equals P times M. B equals Q times S. Right? This case you didn't mention. And N is also, yeah, in this case, N is also P times Q. Right? But this time, A equals P times M, B equals Q times S. But in total, P times Q, that's N, right? That's N. Can divisible to A and B, right? This is P times M times Q times S. That's the case I made up from here, 6, 10, and 21. So this here, we have factor P from A, factor Q from B. So it covered all the factors of n. Yeah, that's the say one thing missed. Yeah, a whole you missed. Yeah.
Okay, I get it. So
Okay?
it's just I didn't really prove that
Right.
if B had partial of it and A
Yeah,
had
yeah,
partial,
yeah, right.
then
Yes.
I only proved that if B has partial and A has partial, they're co-prime, not that they're divisible.
Oh, yeah, yeah, that's right.
So
Yeah.
I did that they're co-prime. Oh, okay, I
Co-prime,
get
only
it.
co-prime. Oh, okay, yes. Right.
So 1A is false and 1B is true.
Yeah, yeah, yeah. Okay, that's right. Okay, good.
Wait, can we prove 1B by stating the same thing about the prime numbers? And
Yeah.
A has partial prime numbers.
Yeah.
And B also has partial prime numbers. But when you put them together, they will have oh, what am I saying? I can still prove it through prime numbers, right?
Yeah, yeah, prime, yes. Just
I can say that A will have prime numbers that n contains, and B will also have prime numbers that n contains.
right.
And you can put them together.
Yes. Yeah.
Okay.
All right. Okay, good. That's nice.
Okay. Yeah.
Yeah. For A, okay, finish. Okay. For B, okay, another one similar to A. Yeah. It is true that A, B, and the same, similar. Okay, A divisible to n, B divisible to n. Then A, B together divisible to n. Okay. Do you see it's a yes or no?
I think it's yes for this one.
Okay, it's yes. Okay. What's your proof?
I think that the proof is if we do the prime numbers thing again.
Yeah.
N will own partial prime numbers of A and
yes.
also partial prime numbers of B.
Yes. Yeah.
And since they own partial prime numbers of each, it will be divisible if you put them together.
Okay. So did you think of one case? Yeah. N only has say AB has a common factor. Say common factor P doesn't matter P. Okay. But N can only have the common factor P once, not twice. That's another problem. Yeah, your proof is good, yes. But you still missed one case. So this is special. So N contains, say A has a factor P. B also has a factor P. But A must contain a factor P, right? Yeah. It must have P. Good. But for N, there are only one P equal power of 1. But for A and B, each of them has power of 1. So altogether, when A times B, they are power of 2. Right? So
wait.
You will counting example, no problem. I give counting example. So that's A. Okay, let me check. Okay.
I have a question about the sign.
Yeah.
When it's like this dash sign, does it mean that A doesn't mean this?
Vertical line?
Or does it mean this?
Oh, they are not equal. They are not equal. This is square.
Yeah, I'm just saying. With that line, it equals to this one, not this one.
Which question?
I'm saying like so let's say A this n, this will just equal to this.
Let me see.
So n divided by A.
Oh yeah. Okay, that's right.
So it does.
Yeah.
So it does.
Yeah, right. N divided by A. Yes. N divided by A. Yes. Right.
Oh, so it doesn't mean this.
You're the right one. Right one is the big one. This is a big one. Divided by the left one.
Oh, so I've been doing the wrong way. I've been doing it the wrong way when I'm proving it, because I'm saying that n is the smaller one.
Wrong way. So this is correct. This is the first one. So this one wrong. So A, B. That means 3 one here, big one there.
Yeah.
That's the wrong way. Oh, that's the problem. Yeah, that's the wrong way. Okay. So always use the you just put the say divide. Yeah.
Yeah, I think I'll try it again after.
Yeah. Try again. Maybe try again. Yeah. Good idea. Yeah, try again. No problem. Leave it for next class. Okay, no problem. Try again. I just mark it. Okay. Okay. I just mark it. So this one done. Okay. First one done. Okay. Second one mark it. Okay. Now. Okay. Next easy one is 3. 3 is the easy one. Yeah. Do you have answer for question 3 proof?
I haven't tried that, but I think I can do it.
Yes, please. Yeah.
Let's do it. It's like I think it's like there's probably a pattern. I guess I haven't done it yet.
Yeah. Yeah, it's a pattern. You're right. It's a pattern.
661 divided by 7 will
Yeah.
give us 963, 3, 1, 4, 28, 3, remainder 3. 66661 divided by 7.
Yes.
We'll get 9, 336, 530, 51114.
We can do calculation. You're right.
This 666, 7, 9, 63, 36, 5, 35, 1, 6, 2, 14, 21, 3. So the remainder 0.
Yes.
I think the pattern is remainder 1, remainder 5, remainder 3, remainder 4, and divisible.
Yeah, and 0, right? 0 means no remainder.
Yeah,
Okay.
and I think it just keeps on going.
Yes. Okay. Oh, but what's next? After 0.
After 0, 1, 2, 3, 4, 5, 1 divided by 7. I think it will repeat.
No, not repeat it like this way. Not this way.
I think it's opposite. It goes 4, 3, 5, 1.
Yeah, 4, 3, 5. But yeah, 4, 3, 5, 1. But after the 1, it's not 0, I think.
It goes 1, 5, 3, 4, 0.
Okay, yes. Then go back to that 1, 5, 3, 0. Yeah, this is correct. So
Yeah.
now we repeat this part again and again. Yes. Let's check. How many? So there are 4. No, something may be wrong here. 4 then. Or 1, 5. Okay, let me check. So this is 1. You said 5, 3. Oh no, it's not this way.
Maybe it'll go. Maybe it goes 1, 1.
Okay, this is not correct. This is not correct here. Too many.
Okay.
No, not 7. Okay. So
I think there should be like another 1 in between.
Yes, another one. Not this one. Not this one. Yeah, another one.
So I think like
Yeah. Use this method to solve the problem. Yeah, you're right. Use this method. This is one of the methods. Yeah.
Yeah.
Find the remainder.
Maybe I can use arithmetic. Modular arithmetic.
Yes.
Oh, I think I can, because I can say 1 is congruent to 1 mod 7, and 61 will be congruent to 60 plus 1.
Yeah, 60 plus 1. Yes.
Mod 7.
So
then I can get
for 60. Yeah. Then plus 1. Yeah.
So I can get 61 will be congruent to 1 plus 4 mod 7.
Yes, this is a good one. Yeah, that's great.
And then I can do 661 be congruent to 600 plus 61.
Yeah.
Mod 7, which then will just be congruent to 600 divided by 7, we get 856.45. We get remainder of 5. So then we get 5 plus 5, we get a remainder of 3. But I think what we can do is that we can show that 60, we can just find 60 to mod 7 and then 600 to mod 7.
Yeah, yes.
And then 6,000 mod 7.
Still no pattern, right? Still different. You find each of them, right?
It probably will be a pattern. I think it'll be like a 7-digit repeat.
Yeah.
Some calculation.
Yeah, yeah. Divided by 7, yes. Find the module.
3 divided by 7.
They are all different. Yeah, they are all different. Yeah, they are all different. So this work is same as just use this number divided by 7. I think it's same. Same. You didn't say make it easy. Same workload. Workload.
Wait. So
Maybe you can try the 6, all the 6, not just the 600 or 6,000 something. Try some 6, put together, see where something happens. Because we want, then add a lot of 6 in the front, right? And maybe you can try the 6, all the 6s.
Remainder 5 is the first one.
Using put it all together, find the module. Yeah, that's better.
Yeah.
Yeah.
I think I'll just prove it with like a pattern. There probably is a pattern.
Yes, it is. Yeah, there is a pattern. Yeah, right.
So it's remainder 1, remainder 1, remainder 5, remainder 3.
Yeah.
And then remainder 4.
Yes.
And then remainder 0.
Yeah, we find 1. Yeah. So this is the first one. So 6, 6, 6, and 1. This is the first one. Yes. Yeah, right.
Oh, and then we get remainder of 2.
Yeah, that's different. That's different. Yeah. So the remainder should be 2, right? 2. Yeah. So we need infinite.
We get remainder of 1. We can add another 6.
Yeah.
And we will get a remainder of 5. So it's repeating. It goes 1, 5, 3, 4, 0, 2.
Okay, that's good. Yeah.
And I can just prove because of this pattern, it works.
Yeah. This is a pattern. Good. Yeah, right. So if I keep going, so after every 6 of them, we have a new number. It's divisible by 7. Yes. That this is a common difference sequence. That's infinite.
Yeah.
Infinite. Yeah. Good. Good. Yeah. So this is one of the methods. Another method. Okay, we just find this one first. This is the first one. Now we can check this number. It's made by 6 of 6, right? So this one can be divisible by 7. So this one is 7, 9. Okay, 5, 25, 16, 2, 26. 21, 56. Yes. So while we have 6 of the 6, it's divisible by 7. Now, what do? We just add another 6 of 6 in front of its base number, right? So every time, the same as your method here, every time I just add this one in the front. So this as means this one times, right up here, this one, that means this one times 10,000, right? 10,000.
Oh, so it's infinite because you can keep on adding six sixes to the first.
Yeah.
Oh.
So this one is divided by 7. Also, this one divided by 7. So every 6 of them, 6 of 6, it can divide by 7. So we keep adding. That's infinite. Do this way. We don't need to find out any other remainder. Just find each part. So every new number we made by the each part add together. That each part is divisible by 7. So all the numbers should be divisible by 7. That's the way. Yeah, every 6 of them.
Oh.
Yeah, keep going. Yeah, this is another method. Yeah, yours is also good. Yeah, find the pattern. Okay. So I just show you this method to find the infinite. Adding. Yeah. Same way to adding 6. 6 of. Yeah, got it? Yeah.
Yeah.
Yeah, that'll be really good. Okay. You also find the correct one. Okay, good. Yeah, this one down. This one down. Okay. Which one do you want to do next? Number 2 or number 4?
Number 4, I think.
Number 4. Yeah, number 4 is good. Yeah. Okay, this is International Mathematics Olympiad, IMO. Wow, very famous one. 1959, but old one. This is, if you know the answer, it's not too hard. Okay, another proof. A lot of proof. Yeah. Irreducible. Do you know this? What does that mean? Irreducible. Yeah, that's a keyword for here. Yeah.
Irreducible means like you cannot simplify the fraction when you plug n in.
Right. Yeah. Right. Yes. Say for example.
So this is really simplest base.
Yeah. So this one is reducible, right? This one equal to.
Yeah.
Yeah. But this one done. It's already simply formed. So this is irreducible. Okay. 7.
I think the number will be irreducible if the bottom number is a prime number.
Yes. If one of the number is prime number, doesn't matter the numerator or denominator. Yeah. It should be.
I don't think so, because if the numerator is a prime number, let's say 7,
right.
The bottom could be 14, and then we can simplify to 1/2.
Yeah, right. Yeah. Okay.
So I think it's the bottom. The bottom must be a prime number for it to be irreducible.
Have you checked the n with different n, the bottom one? Maybe it's not prime, or you check everything is prime.
It's always prime.
Okay, why n is 1?
3, 42. Wait, no, it doesn't work. It's not always prime.
Not always right. No. Well, n is 1 is good, 17, good. N is 2, 28, 31, good. N is 3, 45. The problem is when n is 3. When n is 3, it's 45. And 45 is not prime number.
Yeah.
Yes?
Oh, I think
that's the problem.
I think what we should write is that they both can be a prime number. However, they can both be a prime number. However, if the numerator is a prime number, then the numerator cannot divide into the denominator.
Right, you're right. Only one of that. If one of that is prime number, it's fine. It cannot go further, right? If the top is prime, say 7, bottom can be 100, and also can be 60, or it be 24, doesn't matter. As long as one of that, top one or bottom one, doesn't matter. If bottom one is 7, top one can be, say, 50 or something. Yeah, it's irreducible, right?
I think we can first prove that 21n plus 4 cannot divide into 14n plus 3.
Okay. Yes, that's another way. Yeah.
If we do that, then we can see. Then we can let both prime numbers just be prime numbers.
Yeah.
How can we prove that?
This is another way. Or another thing, co-prime. Yeah, like you said before. if top and bottom co-prime, yeah, it also cannot.
Yeah. That's the thing. Yeah.
Yeah, good, yeah, co-prime. Okay, good.
Yeah.
That's it. Yeah, how do you prove this? Yeah, there are two.
I think we can use algebra maybe.
Algebra, yes, you can. There are two different ways. One is go directly, another is go indirectly. The opposite way.
Yeah.
Opposite way, okay. Yeah, so one method is find the factor of them. So we can prove there are no factor greater than 1. That's it. So the GCD of the top and the bottom equals 1. Common factor, right? The GCF or GCD divided is 1. That's the method. Another way, say we just say assume it has a factor p greater than 1. Then find what happens.
Yeah.
Whether p exists or not. Yeah, if something exists, then it's irreducible. And not find the common factor. That's two different ways. Yes. Okay.
Yeah.
If you have some idea.
Oh, hold on.
Oh yeah, I'll give you some 1 minute or 2 minutes. Yeah. Yeah, just show you the two different ways to solve the problem. Both are correct. Both can find an answer.
So we have to prove that the GCD of
yes, this
21 n plus 4 and 14 n plus 3 must be 1.
Yes. If GCD is 1, that means it's co-prime. Right? Yeah, good. Yeah. That's the way. That's the method we.
How do we prove it? That's the question.
That's the question. Yeah, we have to use some real number. Okay, we have to prove this one, right? So if we have a real number, like the simple one is easy, right? The 6 and 9. That's so easy. GCD. What is GCD of 6 and 9? Find some real example. This is easy, right? Okay, if this is GCD 50 and 93, a little bit hard. The number can be, so we find the common method. How to find the GCD easily? Using the common method to apply here, then I find the answer. Yeah, what's your method to find the GCD 6 and 9?
I think I prime factorization.
Yeah, factorization. So 6 factorization is 2 times 3, right?
So we can prime factorize 21 n plus 4.
Yeah, so the both of them have the common one, 3. Yeah. So 3 is a good one. Yeah, this is one of the methods. But for this method, because for this one, we cannot do factorization. 21n plus 4. 14
Yeah.
Yeah, we cannot use. Or for this one, the hard one. So if I give you a big number, say the 1, 2, a big one. Yeah, we just have to find out some simple one. Can use on this article easy one. So 1, 2, 5, 3, 6 are too big, right? 6. And another one, say 9, 8, 7, 7, 6, 5. What's the common factor of these two numbers? So this is a little bit harder because it's a big number. To do factorization is not easy.
Yeah.
Yes. Yeah. Do you have other methods, or did you learn the method to find GCD?
GCD.
Yeah, another way. If a big number, it's hard to do factorization, like the algebra expression 21n plus 4.
Oh yes. I think I know.
Remember one of the methods.
I just learned it like a few months ago. I can't really remember.
Really?
It's like the big number subtracts small number,
Yeah, right. Subtracting. Yes, yeah, right.
and it keeps on going.
Yes, it is. Okay.
I
Okay,
think.
actually, how to do this one? Yeah, yeah, right. So, like,
So let's say
yeah, GCD
9, 8, 7, 6,
9,
5.
your big one, 9 minus 6. So the answer is 3, right? So this one, because we just using the difference to replace the big
Yeah.
one. So this becomes equal to GCD 6, keep it right. Then 9, we can replace the difference with the 9. So it becomes GCD 6 and 3. Now keep going.
So when we do 9 subtract 6,
yeah.
I think it'll become 3,
Yeah.
but then the other one will still be 6.
Yeah. So 6 minus 3 is still 3. But another one leaves it there. No point, no change, right? So,
then we just continue that.
Yeah, continue that. Right? And
so we have
until the two numbers same. That's it.
21n plus 4.
Yes,
subtract 14n plus 3.
Excellent. Yes, excellent.
Which one's the bigger one though? 21n plus 4?
21 is bigger. 21 is bigger.
Oh yeah, wait, does it say n is a, oh yeah, n is a positive integer, yeah.
Positive.
If it's negative, then it's different.
It's a positive.
It's positive, so, okay. We can get 7n plus 1.
Yeah, you're right.
And then we can do 14n plus 3, subtract 7n plus 1.
Yes. So we leave the and the small one, right? Yes.
Yeah, and then we can get 7n plus 2.
You did well. So this one
and then the larger one will be 7n plus 2.
Yes.
Subtract 7n plus 1 will give us 1.
Yeah. Okay. This is
the GCD's 1.
Yes. Done. That's the proof. Excellent. You did that. Very good. Okay. That's one.
I remember I learned that somewhere.
The GCD is 1, yes. Because 1 will not be the 1, right? So the GCD always be 1. So that's the proof for this one. Done. Right? So this is one way I said. There's another way. I'll show you another way. Okay, another way is
so much easier than I thought it would be.
Yeah, this is much easier. If you find the correct method, the easy method, or the general method, it's easy to apply. Done. Okay, another way. So we say, suppose there is a factor P. P is a common factor. Common factor, right? Common factor of both the top and bottom, right? Common factor. Common factor of the top and common factor of the bottom. Now, common factor, we can write down using modular. So 21n plus 4. This one equal to 0 mod P. Because we already say, assume P is a factor, common factor of both of them, right? So 21n plus 4 should be equal to n modulo P, right? Also, we can write down this one. This is another method, okay, to prove. So this one equal to 0 modulo P again, right? And also we have a rule. So both sides times the same number is unchanged, right? So say, for example, 6. Okay. Okay, modulo 3. Okay, modulo 3. Okay, has say remain the same, 0 and 6, right? This is same. So now we just times together the same both sides. So 6 times 2. This is 12. 12 divided by 3. It's same. Still gets the remainder 0. Right? So it doesn't change. If this number times 2, that means both sides times 2, right? So 0 times 2 is 0. So this one, fine. Okay. Now we use this method. So the first, this is number 1. This is number 2. So number 1 times 2, left hand side, becomes 42 and plus 8. This one, congruent to mod P. So this is, this is, okay, no. Then we need to do another change. Okay, for equation 2. So this one times 3. So it becomes 42n plus 9 equal to 0 mod. Now, this is 4. Then we use 4 minus 1. Minus 3, sorry, 4 minus 3. It becomes 42n cancelled, right? It becomes 9 minus 1. The left-hand side is 1, right-hand side is 0. That means a number divided by p has different remainder. Not possible. Right? Using this method, this is how to find the contradiction, right? Find the contradiction.
Yeah.
That means the p is not possible. Yeah. So it goes the opposite another way. That means because at the beginning we say assume p is a common factor that's greater than 1, right? Yeah. At the end, we find this not possible. We cannot find this one p. We cannot find this p. So we don't have the common factor. That's another proof for this question. Okay, that's good. Yeah.
Yeah.
Okay, good. Yeah. Yeah. Wow. Okay. Number 2, right? Number 2. Yeah. Proof. They are infinite. Okay, another infinity. Many primes of the form 6n plus 5, where n is a positive integer. Okay. Do you think of this question? Yes, it's very hard because infinite prime numbers. If it's limited, we can write down like this. Some other question, write down everything. But this one, you don't have proof. Unlimited, yeah, infinitely. Yeah, see if you can get something. Yeah, n is a positive number. Yeah, can be 1, 2, 3, 4. Yeah, anything. N can also be n is 0. It's also a prime number. Fine. Prime number, yeah. How do you prove it's a prime number?
Prime number.
Yeah. Using the definition, prime number is a number. It only has 1 and itself as a factor, no other factors. Yeah. That's the prime number.
So we can just find that 6n plus 5 doesn't have any multiples.
Right. Yeah, right. Yeah. No factors greater than 1 and less than itself. Yeah. It has some other factors. If we don't have other factors, it's fine. If it has other factors, it's complicated.
But this question's a bit hard because it's quite hard to prove that there are infinitely many primes.
Okay, we just.
It's hard to. I don't know why it's hard to prove infinity for me because.
Yeah. But
well, I can just make the statement that. Yeah. Everything is infinite, so there's an infinite amount of things.
Yeah. Okay, but we proved that number 3 infinite. Yeah, this one we did very well. Number 3 infinitely. Many numbers divided by 7, right?
Or
this one was done.
There might be a pattern.
Yeah. So this one we're using the pattern. Yeah, using pattern. But will there be some pattern for this one or not? Maybe not. Yes. This one pattern is good. Yeah. And no pattern. How do you do that? Yeah. If we check if there are some pattern. If we can find a pattern like n equals maybe say n equals 2 to the power of p, maybe something, right? Or n equals maybe 3 times 5 times some m maybe. Can you find a pattern or not? If we cannot find a pattern, we have to use another method. So always first time we use the method of pattern. Now if no pattern, we can use other method here. Because pattern is very easy for us here. Like try to group here, use pattern. Maybe not. Yeah, just try it. Or maybe you can find just try n equal maybe n equal 1, or what happens? N equal 2, what happens? See, is there any the prime numbers has some pattern or not? Maybe not here. Maybe yes.
I think the thing I found is that
Yeah.
if we know that 6n plus 5 has to be odd.
We should there. This must be all numbers too, yeah. Because
Yeah, which means that it cannot be divided by 2.
right. Not divided by
And it cannot be divided by. It cannot be divided by 3.
yeah, not 2. Okay, not 2. Okay, not 3. Yeah, you're right.
Yeah.
Not 2, not
And it can't be divisible by it can be divisible by 5.
yeah.
But the only possibility is when n is divisible by 5.
Yes.
But
Yes.
since there are infinite amount of numbers, we don't have to care about that.
Yeah, you're right. So why about this one? Yeah. We only
So
need, doesn't matter when everyone. So don't need any
Yeah.
more. Only
and 6n plus 5 is not divisible by 7, I think.
okay. Good. Yeah.
And it will not be divisible by 11 because or it can be divisible by
Yeah,
like 11 if n is 1.
But n is 1. Yeah. But fortunately, 11 is a prime number. 11 is prime number. So afterwards, all the words greater than 11 and divided by 11. That's not prime number. Yeah, only 11 is prime number divided by 11. All others not.
Yeah, so well, not divisible.
Okay, that's right. Okay, because there are how many prime numbers there are? Is that
Infinite prime numbers.
yeah, limited or unlimited? Yeah.
So as long as we see that,
Finite.
even if it's divisible by a number,
Yeah.
it can't be every single number that is divisible.
Right. Right.
Because we can just not care about that because there's infinite primes.
Oh, infinite primes. Okay. So you mean because we cannot divide by all numbers? So you mean the total?
There might be cases where it's like divisible by 5. There'll be infinite cases of that, but there'll still be infinite cases where it's possible because there's infinite numbers.
Infinite numbers.
Infinite subtract infinite is infinite.
Yeah, but you cannot prove by using infinite to prove infinite.
Yeah, I feel like mine's not really not really working.
This is a very interesting question. The question is very easy.
Yeah.
The method is similar to prove the infinite prime number. Due to the method, how to prove there are infinite prime numbers? Nothing is proved. Okay, if the question comes to prove that there are infinitely many prime numbers. Can you prove this one? No, these conditions. Only the first part. The method is the same. They prove there are infinite primes. Infinitely. Do you do this one before or not?
No, I haven't.
No? Okay. So, but I heard you said there are infinite prime numbers, right? You know that?
I know it's infinite primes. I can't really prove it.
I can't really prove that. Okay. Okay, that's okay. That's okay. Okay, we'll go back to this one here first. So, first step, we have to divide the integers into different groups. So 6n plus 5, just one of them, one of the categories. Okay. So for others, I can divide all the numbers into all the categories. So first is 6n. Next, 6n plus 1. 6n plus 2. 6n plus 3. 6n plus 4. And also the last one, 6n plus 5. Is that correct? Every number must fall into one of the categories, right? One of the groups, right? Yeah, each number can. Just one of them, right? Yeah, that means the number divided by 6. The remainder is 0, 1, 2, 3, 4, 5. Okay?
Oh, yeah.
Yeah. Yeah. Using the remainder, find the different remainder, right? Yeah, that must be in one of them. So 6 plus 5, just this one. Then we check each of them. How about prime numbers? So 6n, is 6n prime number?
No.
No, this one is no, okay? This one no. Okay, don't worry, 6 plus n plus 1, okay. Next thing, we just find out all the case is not prime number. Now, next one is 6n plus 2.
It is a prime number. It can be.
It
Oh
can
wait, 6n plus 2.
Yes.
Oh, sorry. 6n plus 2 cannot.
not.
Unless n is 0.
Another no, good, another no.
But 0 isn't a positive integer.
Yeah, yeah, only 0, yeah, but 0, you are right.
Yeah.
Okay, no worries.
How do you say isn't an element?
No worries. Say we can say n is greater or equal to 0. Okay, no problem. So if in this case there are only 2 as the prime number, except 2, there are any other prime number? Except 2, no problem. It can be 0. It's still okay. We can,
6n plus 1 could be a prime number.
okay, yeah, this one could be, yeah, could be prime. Yeah, right.
6n plus 3 can't be prime. It can be divisible by 3.
Yeah, only 3. And any more? Except 3. Any other prime numbers from 6n plus 3?
No.
Okay, no, right, yeah, right. Okay, now 6n plus 4.
Apart from wait, there's no.
Yes or no? No, definitely no, right?
No.
No, but even if n is 0, it's 4. It's not prime number. Okay, then there we need proof. There may be some prime number. Yeah, you're right. Part of them prime number.
Yeah.
Yeah, that's very clear. So we can see all the prime numbers are from 6n plus 1 and also 2 and 3. That's all the groups. The prime numbers fall into this group. So we need only think of these cases. Yeah. Now it's better for us to prove that. So it's prime number only 4 into 6n plus 1, 6n plus 5, and maybe 2 or 3. This is limited, doesn't matter. 2 or 3 doesn't matter. These 6n plus 1 and 6n plus 5 are the big groups. Yeah, you're right. These are
Yeah.
so,
So pretty much for this question, we just proved that there are 6 categories: 6n,
yes.
6n plus 1, and 6n plus 2,
Yeah,
6n plus 3, 6n plus 4, and 6n plus 5, and then we find that they're prime.
Because if there are no numbers, no prime number here, that's very easy. So all number must be 2, 3, or everything must go there, right? If these are this is no, this is all complete numbers. The question very easy, right? Every number must be here. Done. We prove.
Yeah.
But unfortunately, we have some prime numbers. We don't know how many. Maybe infinite, maybe limited. Fall into this group, 6n plus 1. Now you have to prove there are infinite numbers fall into this one, and some of the number here. That's the trick to prove that.
Yeah.
Yeah, that's probably. That's for the hint.
So we just have to prove that they're infinite primes.
Yes, infinite primes. Yeah. So we have 2 groups. Unfortunately.
And then we can.
Yeah. 1 group is easy, done, finished.
Yeah.
But 2 groups too hard. Yeah. Because you already know there are unlimited, infinite prime numbers in total, right? So yeah. The total prime number divided into 2 groups, like we said, 6n plus 1, 6n plus 5.
Yeah.
Okay.
Okay.
To solve this problem. Okay. Let's just for study hint. Okay. We don't have time today.
I think I get it.
Yeah. We are thinking over from this, right? From this, you think over. I give you proof next class.
Yeah.
All right.
Okay.
Yeah. All right. Okay. You think it over. Okay.
Thank
For a
you.
while. If you cannot think it out, no problem. Yeah. I can solve it next class. No problem.
Yeah.
Okay. Good. Yeah. Okay. Thank you. All right.